This is part 4 in this series on the Wren computer project, in which I'm attempting to not only repair a number of Wren computers but also reverse engineer the firmware and the hardware. In the previous video I was looking at reverse engineering the code for the floppy drive controller, and part of this series is going to jump about quite a bit because as I go along I want to try and effect some repairs on this machine so that we can more successfully reverse engineer the firmware. And if you recall from the previous video, I was looking at determining the addresses of the internal registers and how they were mapped into the hardware system, and we found that the registers were mapped to addresses. These are port numbers 28, 29, 2A and 2B. However, we never got a hit on register 2B, which is, if you look at the spec sheet for the device, it is the data register. So although we were getting responses and data coming back from the other three registers, which are the status, track and sector registers, the data register was never successful in reading data. And I had a look at that because I wanted to try and get to the point where the floppy drive controller was at least reading some data in order for us to more successfully progress with the reverse engineering of the hardware as well. So in order to do that, I had a quick look around to determine why it was not reading any data from the floppy drive, and it was doing the same thing whether I used a physical drive or the Gotek emulator. And it turned out that the had a device back here, a 74 LS32, that wasn't really working very well. It tested okay in the IC tester, but the output wasn't high enough to successfully drive the A0 and A1 lines properly on the floppy drive controller chip. So I've replaced that. It's this device here. The eagle-eyed among you will probably note that I haven't fitted an IC socket to that. I normally do when I replace ICs. I can't do that with that particular device. This board, when it's in the machine, has a bar fitted to it. It's got this bar bolted along the rear edge, and you can see there's a hole here. There's one in the center and one on the other side, and this is a hinge bar. The entire board hinges inside the machine. But unfortunately it means there's only this gap between the inside of this plate and the PCB, and so there isn't enough height to use IC sockets along this rear edge. So any devices I change back there, I do have to solder them directly to the board. So I've replaced that device. I found a broken track as well. The track issues on this board are fairly bad because of the location of the battery, and when it fails it tends to do a lot of damage to the board. So I had an open track as well, so I've also fixed that. So we'll now look back at the logic analyzer and see if we've made any further progress before we go back into more detailed analysis of the board map layout. Okay, so looking back at the analyzer screen, what I have here in the trigger setup is the read enable line looking for a 0, chip select looking for a 0, and the A0 and A1 lines looking for a 1-1 sequence. And the A0 and A1 lines are these two lines on the controller chip, and when they're both high we're selecting the data register inside the floppy drive controller. And because we're also looking at a low on the read and a low on the chip select, then what we're actually trying to trigger on is when the data register in this device is being read. And in the previous video we saw that that was never happening. So we'll try it again and see what happens. We'll go to waveform, we'll arm the analyzer, and I'll press reset on the Wren. And you can see this time we are successfully getting a hit. Not only that, but the data that we are reading from the floppy drive controller, you can see here if we look at the control lines, we're getting chip select going low, and then a short time later we are seeing a data value appear on the data register and also on the DAL. DAL is the data output bus of the floppy drive controller chip. They're both showing the same value, so we know that the data between the two is not inverted, at least not outside of the Z80. So the question is that a valid value? And if we look at the first few bytes of the software, so this is the data on the actual floppy disk itself. This is not the firmware, this is the floppy disk data. And this is the start of the first sector, and in theory we should be starting with this value and then reading sequentially through the first sector. And this is the first track, by the way. So we got the initial value of CE, which obviously isn't 31, but if you recall in the previous video I also said that the WD2791 has an inverted data bus. So if we take the value of 31, so I'll get my trusty calculator here, 31 hex, I've got this in hex mode. If we invert that value, so I'll XOR it with FF to invert it, we end up with a value of CE. And if we look on the listing for the floppy disk itself, we'll see that the first value is in fact CE. So 31, in other words, is the correct value that we should be reading from the floppy drive. Remember, the value on the drive itself is not inverted, it's just the data bus is inverted. So that value is correct. So the question is the next value correct? So the next value on the floppy disk should be 7E. So what we'll do is we'll change the trigger on the analyzer to capture the next value. We can't just set this to 2, although it's set to trigger on one time event, so the first time we see the event that we've selected it will trigger. But if we look at the waveform, you'll see that we actually have a number of clock cycles showing the same value, and if you count these, and again on the way I've got the analyzer set up, I'm triggering on both rising and falling edges. So each of these divisions is a clock edge. This is the Z80 clock we're talking about, because that's what I'm using for the state analysis mode for the analyzer. And if we actually count these states, we'll see there are 12. Okay, so what we need to do in the trigger is to set the number of hits on this particular event to make sure that we select the next value that's read from the floppy drive controller. So we're getting 12 clock edges from the Z80 clock between the data value being read and the next event on the data bus occurring. That's when the trigger will stop being hit on the analyzer. So what we need to do is to change the number of hits so that we exceed 12 full clock cycles. So for example, if we go to 7, then that should give us a hit on the next data value being read from the floppy drive controller. So we'll rearm the analyzer. I'll press reset on the Wren, and what we're getting now is a value of 81. So if you recall, we're looking for a data value of 7E, but again the value is inverted. So if we take 81, which is the value we've read on the data bus, and again we will invert that, we get a value of 7E, and that is correct. So we'll do another couple. So we'll change the trigger again to make sure we capture the next value read from the floppy drive controller. I'll reset the Wren, and we're getting a value of 02. So same process, 02, again this is in hex. We'll invert the value and we're getting FD, and if we look at the output from the floppy disk listing. You can see the next one is FD. We'll do one more. We're now getting CD, so CD, if we invert that, we get 32, and looking at the listing, we do indeed get 32. So we can see that the board is now at least able to read data from the floppy disk, and not only that, but it seems to be reading the data correctly. The Wren, however, still isn't booting. It's still doing exactly the same thing it was before, and it does seem that until it gets through quite a large proportion of loading the data from the floppy disk, we're going to get the same issue arising. Just sits there without giving us anything meaningful on the screen of the Wren. Just seems to be the way that the Wren's configured. So what we'll do in the next video is we'll break out the Fluke 9010A, and we'll start doing some testing of the devices on the board, and that will enable us to eliminate some things. This sort of non-booting could be pretty much anything, so we need to start eliminating some things, and also this will give us a very good heads up for looking at the reverse engineering of the firmware. So thanks for everyone that's contacted me so far. And as I say, once I've got some decent information put together, I'll put the files on my website, and then hopefully we can all get involved in trying to create some meaningful support documents for the Wren. And also, as part of the process, of course, try and get at least one of these Wrens up and running, so we have a good test platform to use.